My name is Andrew Vogel, and my project is predicting tweet engagement with deep neural networks. The 30-day prevalence of e-cigarette usage among 12th graders is 16.2%. Smokeless tobacco is 2.9%. Conventional cigarettes is 11.4%. I wanted to answer this question. How can health agencies improve engagement on social media, specifically Twitter, where engagement is the sum of likes and retweets? Interpretable machine learning provides insight into why a certain prediction is made. I can look at why that prediction was made and extrapolate features that make a tweet engaging. Then I can use these features to create engaging tweets. For example, if tweets that talk about lung cancer in young adults are more engaging, it would be beneficial to tweet about said topic. The goal of my project was to use interpretable machine learning models to predict tweet engagement. A machine learning model, in this case a differentiable model, is just a large objective function that inputs weights in data and outputs a prediction. Weights are trained values that interact with data by means of multiplication, addition, division, etc. to produce an output, or prediction. When evaluating and using a model, the weights don't change. However, when training the model, the weights do change to make better predictions. I have several diagrams like the one below in this presentation. The boxes represent different types of functions, and the arrows represent what they feed into. The first model I used was an attention-based long short-term memory network. LSTM networks are typically good at understanding natural language due to their cyclical nature. LSTM networks are meant to possess a deeper understanding of the text rather than picking important words or phrases. What makes this network interpretable is that it uses an attention mechanism. Within the function, an attention value is computed for each word that indicates how important its context is. This isn't a direct reflection of how important a specific word is because of how an LSTM transforms data. However, it is useful for extrapolating features that are indicative of an engaging tweet. Here is a diagram of the attention-based model. I used bidirectional LSTMs because they can provide both forwards and backwards context for a word. Next, I used a convolutional neural network. CNNs are usually used for tasks involving image recognition. However, I repurposed them for use in natural language processing. I used a one-dimension, one-convolution CNN with 300 channels of varying kernel size. CNNs create feature maps that indicate which areas of an image, or in this case a sentence, are important. Here's its diagram. I can't just stick the text of a tweet into a model because words aren't numbers. First, I have to pre-process the text and somehow transform them into numbers or a vector of numbers. To do this, I used latent Dirichlet allocation, n-grams, global word vectors, and metadata from the tweet. Each word has one of these, which is what is fed into a model, which makes the model to make the prediction. Latent Dirichlet allocation is a topic modeling algorithm that gives the likelihood of a tweet belonging to various topics. In my case, this might indicate whether a tweet focuses on cancer, gum disease, cigarettes, etc. Topics are generated by the machine and can be anything. Sometimes they aren't even interpretable by humans. N-grams are just a string of words n many words long. For example, do-re-mi is a 3-gram or trigram. An n-gram vector is just a very long list of ones and zeros that indicate whether a certain n-gram is present within a tweet. I get the n-grams by looking through the tweet corpus for 1 through 3 grams that appear more than 10 times. Next, I go through each tweet and create an n-gram feature vector for that tweet. I also used metadata, which is just a binary vector where the values indicate a certain meta feature, such as whether or not the tweet contains an image or a link to an external site. Finally, I used global word vectors to create a matrix representation of the tweet. The LSTM and CNN I used perform operations on matrices. In order to turn a tweet into a matrix, I need a list of vectors that represent words to then concatenate into a matrix. Glove vectors are a type of pre-trained word vector that I can do this with. Glove word vectors are global word vectors trained on existing materials such as Wikipedia, or in this case, I use the Twitter glove word dictionary. I extracted these features from my dataset, which includes 4,417 tweets crawled from the @FDA to Twitter address. This data has a lot of outliers and zeros, so I needed some way to deal with that. On the right is a histogram of the data. You'll notice there are a lot of zeros and there are a couple outliers in the 300s and 200s range. To deal with this data, I changed it from a count regression problem to an ordinal classification problem. Ordinal classes are just classes that are interrelated through an increasing value of some sort. For example, hurricane intensity categories are ordinal classes because a hurricane of class 5 is necessarily more intense than a hurricane of class 4. This removes my zero inflation and outlier problem while still providing meaningful predictions. To create the ordinal classes, I bin the tweets by tweet engagement percentile. I used special loss and output functions to deal with this type of data. Instead of giving a single output from 1 through 5 indicating what ordinal class a tweet belongs to, or a vector indicating the likelihood of a tweet belonging to various ordinal classes, my network's output is a series of binary classifier values indicating whether a tweet exceeds a certain specific and unique ordinal class. I concatenate this into a vector, then count how many of these values are greater than an arbitrary threshold to get out an output class. I use this method because the loss function I use necessitates it. Loss is a single number that indicates how well a set of weights can predict correct results. To train a network, you append a loss function and optimize the network with the loss function by changing the weights. This process is done through gradient descent, which necessitates that the network being trained must be differentiable. To have a differentiable ordinal loss function, I used a series of binary classifiers as mentioned earlier. To calculate the loss, I encode the ground truth value for each tweet as an ordinal encoding vector, then calculate binary cross entropy loss on all of the binary classifiers with the encoding vector. Next, I sum these values together to get a total loss. This loss function is important because it represents the ordinal nature of the data. With conventional loss functions, a guess that is off by the maximum amount of ordinal classes is just as bad as a guess that is only off by 1. With ordinal loss, a guess that is off by the maximum amount of classes has a very high loss, whereas if it is only off by 1, it has a very low loss. I optimized my models with the Atom optimizer using this loss function. To evaluate, I must use an ordinal evaluation metric. I use normalized macro mean absolute error. This gives a value from 1 to 0 indicating how well a certain model predicts data, ordinal data, with 0 being a perfect score. Normalized macro mean absolute error scores are not influenced by bin size or number of bins. The CNN performed the best with a score of 0.291, and the logistic regression performed the worst with a score of 0.329. All of the models performed better than random guessing. Here's an overview of my process. I created the models that predict tweet engagement. I trained the weights for them using tweets from the @FTA Tobacco Twitter address. And then I evaluated the models using the normalized macro mean absolute error evaluation metric, using tweets that I did not train on. The CNN performed the best. Words within convolutions that had high values were mostly content words such as tobacco and smoking, which is good. That means I can extract those features and put them in new tweets to create more engaging tweets. I was surprised how poorly the LSTM fared. LSTM networks were created for natural language processing, so I thought it would be the best. The attention values given by the LSTM were uninterpretable and provided no insight. The ordinal classification and loss function worked as intended. And due to the CNN performing well, I think that keyword and phrase recognition are more important than understanding the actual text meaning of a tweet. In the future, I would like to find out why the LSTM didn't work well and how the top tweets algorithm Twitter uses to recommend tweets, which coincidentally uses keywords and phrases, impacts model performance. I would like to thank Dr. Ramakanth Kavaluru, the Math, Science, and Technology program, the Kentucky Young Researchers program, and my friends and family.